Good morning, all. So, good morning, all. Are you able to hear my voice? Am I audible? Am I audible? Am I audible? Okay. So, good morning, all. So, once again, this is the video lecture on design and analysis of algorithms. We are currently discussing with module 3, the last topic, transform and conquer approach. So transform and conquer approach, and till now we have seen divide and conquer approach. That means you are dividing the entire problem what you are having, you are dividing that particular thing and solve the solution in particular time. So now you come for the next method, transform and conquer approach. So in that you are going to discuss heaps and heap sort. Okay, so you are starting with heap and heap sort. So first you come with a word transform and conquer. So there are two stages in a transform and conquer. One is the transform phase, the other one is a conquer stage. So transformation stage, the problem's instance is modified to be, for one reason or another, more amenable to solution. That means the problem instance what you are having, you are solving, you are transforming from one phase to another phase to find the solution. So what happens in the transformation stage? The problem's instance is modified to be, so the problem is modified for one reason or another to find the solution. Okay. So next we come with a conquering stage. So once the the problem's instances are transformed, then you come with a conquer stage. So as and when the problem is transformed and you can easily find the solution, now you come for the conquering stage, it is solved. Okay. So under that, the conquering stage I will tell like this. So problem instance is there. So problem instance has been transformed. That means its representation is changed. So representation is changed here. So that's why we take it as simpler instance, another representation or another problem instance. So this problem instance is being changed to some other type to find the solution. So this is up to here. Changing the problem instance into simpler or another problem instance is called transformation stage. From problem simpler instance, you're finding the solution, we call it as a conquering stage. So this is transform and conquer. There are two stages. The given problem, okay, so given problem is being transformed into given problem is being transformed into another problem and to find the solution. So finally conquering stage. So conquering stage is used, the problem is been solution is been found. Okay, so now you come for the next slide. So heap. Okay, so in transform and conquer we have the first concept where you apply the transform and conquer approach, we are applying it in heap. Okay, so what is heap? So heap is the partially ordered data structure that is especially suitable for implementing priority queues. Okay, so what is heap? Heap is the data structure. As you all know, you have seen min heap, max heap. So heap we have gone through in data structures. The same thing we are going to see it here. It is partially ordered data structure which is suitable for implementing priority queue. Okay, so now you come for what is priority queue. So priority queue is, as you know, queue contains set of items. So priority queue is a multi-set of items with orderable characteristics called items priority with following operations. So how you are going to use the priority queue for finding the item with higher priority, deleting the item with higher priority or lower priority, adding a new item to the multi-set. Okay, so for this purpose you are using priority queue. So after that, now you have understood. So why you are going to use heap? So heap is the data structure that is suitable for implementing priority queue. Okay, so come for the next slide, heap. So definition and its properties. So these are very important thing. So you have to understand this. So there is a compulsory question on heap. That's why I'm telling you, kindly concentrate on heap. So heap can be defined as a binary tree. Heap is a binary tree with keys assigned to its nodes, one key per node, provided the following two conditions met. Okay, so what it is? Heap is a binary tree with keys assigned to its nodes. Okay, so it is a binary tree with a keys. Okay, so it has been assigned to the nodes, one key per node, provided the following two conditions are met. So first one is shape property. Okay, shape property. So binary tree is essentially complete. Understand here. So binary tree is essentially complete. That is, all its levels are full except possibly the last level. So understand carefully. Shape property. The binary tree is complete. That is, all its levels are full. That means binary tree means it should have how many? It should have two children. Then we tell the tree as a binary tree. If each and every node is containing two children, so all its levels are full means all at each level, each node will have two children except possibly the last level. Okay, so possibly at the last level, so where only some rightmost leaves may be missing. Okay, rightmost leaves may be missing. Okay, so left you will be having, so last level also left you will be having, but rightmost leaves will be missing. Okay, the parent, that is the first property, that is shape property. So come for the next one, parental dominance property. So parent is dominating property. So that means the parent should have greater value than its children. Okay, so there are two properties for heap. One is shape property, the other one is parental dominance property. Shape means, so binary tree is completely is complete. So except the last level where only some rightmost leaves will be missing. Okay. So second one is parental dominance. That means parent has the value greater than its children. Okay. So now you come for the next check, which are the heaps. So here you can see. So level 0, level 1, level 2. So level 0 is having 2 children, level 1 is having 2 children. So this is level 2. Okay, so at level 2, the last level, this is the last level you are having. So under the last level, we have one rightmost tree is missing. Okay, so that is the shape property you are having. So after the shape property, now you come for the parent to dominance property. So that means parent will have more value than children. So here parent 10 is having more value than 5 and 7. So 5 is having more value than 4 and 2. So 7 is having more value than 1. So this is a what we tell. So will we tell the figure 1, figure 2, figure 3. Figure 1 has heap. So can you tell is figure 1 is heap or not? Yes, answer here. Figure 1 is a heap or not? Okay, good. It is a heap. So now you come for the second thing. Second diagram. First you see they're telling, so shape property means it should have at least, at each node should have 2 children. So this one is having 2 children, this one at last level. Okay, at last level you have to see, so full except possibly the last level where only some rightmost leaves will be missing. So here you have to see rightmost leaf is missing. So, but here you can see leftmost leaf is missing. Here rightmost leaf is missing. So, shape property is going to pass or fail. So, can you tell for figure number 2, tell whether it is whether it accepts shape property. Is figure 2 accept shape property? Will it accept the shape property? So it does not accept shape property because, so at last level also rightmost leaves will be missing. Okay, so at last level also you have rightmost leaves are missing, but in our diagram you can see at last level leftmost leaf is missing. Okay, so that's why shape property is going to fail, so we can't consider it as a heap. But you come for parent dominance. Parent 10 is greater than children 5 and 7. 5 is greater than 2. 7 is greater than 1. So parent dominance property is accepting, but shape property is not accepting. Understood? So that's why heap, this is not a heap. So come for the third one. So coming for the third one, here shape property, 2 children, 2 children, 1 children, rightmost leaf is missing. Okay, if rightmost leaf is missing, then we can tell it as, it is not, it is a, it accepts shape property. But come for values, okay, parent dominance. So 10 is greater than 5 and 7. Okay, done. So is 5 greater than 6 and 2? So here you tell the parent should be greater than 6 and children. So parent is 5, the children is 6 and 2. So will it accept parent dominance? Yes, tell me. Figure 3, will it accept the parent dominance? Is parent is dominant than children? So here 5 is less than 6. Okay, so at this level you are going to fail. So that's why we tell this is not a heap. Okay, so this is a heap. This is not a heap because of it does not accept shape property, but here it is not accepting parent dominance property, so it is not a heap. Okay, so after that, so now you come for the properties of the heap. So what are the properties of the heap? There exists essentially one complete binary tree. So when you tell it is a complete binary tree, when it has each and every node has two children except the last level node. Okay, so each and every level there is two children for each node except the last level. So here you can see the last level you are not having one right child. Okay, so that's why we consider this as it's a complete binary tree with n nodes. Its height is equal to log n to base 2. The root of the heap always contains its largest element. The node of the heap considered with all its descendant is also a heap. The node of the heap considered with all its descendant is also a heap. So this is the properties. Okay. So properties of the heap. So that is first, second, third. Fourth property, the heap can be implemented as an array by recording its elements in top-down, left-to-right fashion. So this is the heap we have considered. Okay. So under this heap, so you can tell it is recording its elements in top down left to right. So index 0 you don't have anything. So first start from the root node. So top to down in left to right. So first comes 10. Next level you come from at this level you go from left to right. So 8 comes first, 7 comes next. So after that 8 you will get 5 and 2. Next you will get 1 and 6. So finally you will get 3, 5, 1. These are the leaves. Okay, which are the leaves here? So 3, 5, 1, 1, 6 are the leaves. So which are the parents you are having? 8, 7, 5, 2 and 10. Okay, so these are the parents. Okay, these are the parents and leaves we have represented. So now you come for the heap construction. So very, very important concept, that is heap construction of the heap. Okay. So there are two principal alternatives for constructing the heap. One is bottom-up heap construction. The other one is top-down heap construction. So bottom-up as well as top-down. So bottom-up heap construction. Okay. So understand carefully. Initialize the essentially complete binary tree with n nodes by placing keys in the order given. Okay. So then heapify the tree as follows. So how to construct bottom-up heap construction? This is the process you are having. Okay. So start with the last parental node. Check whether the parental dominance holds. So what is the parental dominance? So parent node should be greater than child node. So start with the last parental node. Check whether the parental dominance holds for the key. If it does not, if the parental dominance is not holding, so exchange the node key with a larger key of its children and check whether the parental dominance holds. Okay, so this process continues until the parental dominance is satisfied. Okay, so that is the process of EP5. So EP5 means you have to hold the parental dominance for that. So after completing the EPification, proceed to do the same for immediate predecessor. Predecessor means you are starting from low level, last parental node. So one above the parental node, we call it as immediate predecessor level. You are starting at leaf level. Okay. So last parental means it will be at level 2 or level 3. So adr male iradana pre means above. So that is predecessor. Okay, so algorithm stops after this is done for root of the tree. So understand the example here. So this is the tree. We are going to start it from the last level. Okay, so what is the parental dominance? So child should be less than parent, or you can take it as parent should be greater than. Parent is dominating children. So it is parent is greater than children. So here you start from last parental node is 9, 7 and 2. So 6, 5 and 8 are the leaf nodes. So next level is 9 and 7. So which is the parental node? 9. So is 9 greater than 6 and 5? Yes. So 9 is greater than 6 and 5. So parental dominance will hold. So, okay. So that's why we tell 9 and 6. So 9 is compared with 6 as well as 5. So as it is greater, so now you check. So now you come for this level. Okay. So now you compare at this level, which is the greater. Understood? So after this 9, 6 part, so here you see 6 is lesser than 9, 5 is lesser than 9, and but here 8 is lesser than 7? No. So here parent is 7, child is 8. So here parental dominance is going to fail. So that's why you go with 8 and 7. So here you can see here, so 8 and 7 are replaced. Okay. So after that, now you come with 9. So 9 is compared with 6 and 5. Both children are lesser than parent. So after that, now this level is finished. Now you come for this level. So 9 is greater than 2 and 8 is also greater than 2. So but you come with the leftmost part. So leftmost is being interchanged. So that means 9 goes here, 2 comes here. So here you can see 9 is here, 2 is here. Once the 2 is there, now you are again checking it with 6 and 5. So when you check it with 6 and 5, the children 6 and 5 are greater than 2. So that's why you are going to replace the left child with a root node. So 6 comes here and 2 comes here. So that's why this is the representation what we have taken. So now you have to solve this particular problem. Take it as homework problem. Okay. So now you come for the algorithm part. So bottom up heap. So it constructs the heap from elements of the array using bottom up algorithm. Okay, so what is an input? H1 to n of orderable elements. What is the output? Heap H of 1 to n. So you are dividing it into two. Parent level, the other one is child level. So I is less than I2, n by 2 to 1, k then 1, v then h of k. Heap is false. So now you have to go with children. 2 star k less than or equal to n, j is equal to 2 star q. If j is less than n, that means there are two children. So now you have to check root node with a children node. Root node we call it as h of j. Children is called as a, if root node is less than child node. So okay, so if root node is less than child node, j is equal to j plus 1. Okay, so next if v is greater than h of j, so if v is greater than h of j, if then true, else h of k is equal to h of j. So this is the algorithm what we are taking. Kindly you have to go through this algorithm, understand, write well. Okay. So now you come for the analysis of bottom-up heap construction. So assume for simplicity. So you are assuming for simplicity n is equal to 2 power k minus 1. Okay. So n is equal to 2 power k minus 1. Heap tree is full. Consider key on level 1. For each key moving to next level down requires two comparison. One to find larger child, other to determine exchange is required. So total number of key comparisons is given as 2h minus I. Okay, so how you perform the heat analysis of heap construction? So I equals 0 to h minus 1. level 1 to h minus 1. So that will be taken as 2 h minus 1 to power I. So on substituting I, okay, so on substituting I, we take it as 2. So n minus log 2 n plus 1 by mathematical induction I equals 2 power I. Okay. So thus with a bottom-up algorithm, heap of size n can be constructed with fewer than 2n comparisons. So 2n minus 2 log n plus 1, that we can take it as 2n minus something, we can be taken as 2n. So thus with bottom-up algorithm, the heap can be constructed with fewer than 2n comparisons. So come for top-down heap construction algorithm. Okay, so it constructs the heap by successive insertions of the new key into previously constructed heap. Okay, so first attach the new node. So first you need to attach a new node with a k in it after the last leaf of the existing heap. Then shift k up to the appropriate place in new heap. So the steps for that is given as follows. So compare K with its parent key. If the latter is, you compare key with a parent. If the latter means parent is greater than or equal to K, stop. If parent is lesser than K, swap the two elements and compare K with a new parent. Okay, this swapping continues until key is not greater than last parent or it reaches root. So now you come for the illustration of this particular thing. So this construct the heap using heap top-down approach. Okay, so this is the illustration. The elements are given as here. So 3, 5, 8, 7. So these are the elements. So you have to undergo the particular thing. So inserting the new, this is the tree. Okay, so this tree, it is accepting the shape property as well as parental dominance property. So shape property means, so each level you should have two nodes except the last level rightmost node. Okay, so come for the parental dominance, parent should be greater than children. So now you are inserting a new key 10. Okay, where this will be inserted? At child level you are inserting. So here you can see that at child level, at rightmost part you are inserting. Because this one is empty, you can insert this 10 element 10 here. As it is empty, you can insert the element here. So 10 is been inserted here. So now you check 10 with 8. Okay, so checking 10 with 8. So here child is greater than parent. So replace child with parent. So here you can see 8 comes here, 10 goes there. So this is the thing. Now you compare 10 with its leaf. Okay, its root. So 10 with its parent. So here this parent is lesser than child. So that's why you are going to replace 10 with 9. So now in the last step, you can see 10 goes root, 9 comes here. Once after this, now you can check for shape as well as parent dominance property. So shape means at each level you are having two nodes, and parent dominance, parent should be greater than child. So 10 is greater than 6 and 9, 6 is greater than 2 and 5, 9 is greater than 7 and 8. So that is the insertion of top down. Okay, so now suppose you are going with a delete an element from the heap. So how you are going to delete the element from the heap? So suppose maximum key deletion from the heap. So exchange the root key with the last key, decrease the heap size by 1, EP5. So EP5 the smaller tree by shifting K down the tree exactly in the same way we did it in bottom-up approach. So that is verify the parental dominance. If it holds, we are done. And if not, swap K with a larger of its children and repeat until parent dominance holds for the key K. So this is the illustration. So this is the tree we have taken. Suppose we need, this is the tree. 9, 8, 6, 2, 5, 1. So come for step 1. Okay, so coming for step 1, okay, this is the tree we have taken. Okay, so at this tree, so which is the node to be deleted? Okay, so which one you are going to take? So this is the tree they have given. So for the tree, exchange the root key with the last key of the heap. So which is the root key? Understand here, exchange the roots key with the last key of the heap. Okay, so root key with the last key is 1, root key is 9. So exchange that particular thing. 1 goes there, 9 comes here. So 1 comes, remaining everything is same. Okay, 9 comes here, step 2. Okay, so now after that, decrease the heap size by 1. So heap size by 1 means you are deleting that particular thing. So 1 is have here 8, 6, 2, 5. Decrease means you are deleting that particular 9. Okay, 9 is being deleted. So step 3, after that, EPify the smaller tree by shifting K down the tree exactly in the same way. So now you see 8 with 5. So now you are going to move 8 here and move 5 here. That is shifting the key by. So 8 is greater than 1. So put 8 here and 5 here. So now last step. So 8 will go here. So 5 finally will be getting like this. This is the illustration. So come for the efficiency part. The efficiency of the deletion is determined by the number of key comparisons needed to heapify the tree after the swap has been made and size of the tree is decreased by 1. Since this does not require more key comparisons than twice the heap's height, the time efficiency is in big O of log n. So time there for a top bottom heap, so it was big O of 2n, but here it is big O of log n. Okay, this is up to heap concept. So have you understood? Have you understood the heap construction using both bottom up and top down? Okay, so I hope you have understood this particular concept. So if you have any network issues, you can go through in my YouTube channel 1DPMK. So go through the videos. So go through the videos and have the knowledge of algorithms and all these concepts. So which will be useful for the next coming exams and all. Okay, so kindly like, share, subscribe for the channel. So I will be ending this particular class here. So thank you all. Stay home, stay safe.